All right, so we're going to look at antiderivatives with inverse circular functions. So some prior knowledge for this to understand what this is about would be introduction to antidifferentiation, derivatives of inverse circular functions, differentiation sort of more broadly, and then the derivative of an inverse sine function is something that I explained in a video as well. So I'll put the links for all those videos below. Definitely go and watch those. The concepts we'll cover in this video will be the antiderivative involving inverse circular functions. So we'll just look at sort of the rules for that and hopefully get a bit of a sense of why it's true. Then we'll look at an interesting property of inverse circular functions, and then we'll do a definite integral question. So we'll jump into that. So let's have a look at the first part. A bit of a giveaway here, but antiderivatives involving inverse circular functions basically have these rules. And again, in the previous video, in this video, derivatives of inverse circular functions, if you go and watch that, you'll realize that we came up with the condition that if you take the derivative of these functions, then you get these functions on the left-hand side, these things here. So what that should imply is that if we take the antiderivative of this function here, then we'll get our inverse circular functions. So, we don't have to guess at these things though. So both of these functions are here. So in blue, we've got 1 on the square root of a squared minus x squared. A is currently 1. So it looks like that. And then in pink, we've got sine inverse of x on a. So what we're saying is the derivative of this function, this pink function, is this blue function. So that should make sense because down here, we're getting really large positive gradient values, which is what happens here. And that's why we get this asymptote. And similarly over here, and then it sort of becomes linear here. So it has a gradient of 1 there. So we have an intercept, a y-intercept of the derivative function there. So what we're saying is in the reverse direction, that if we take the antiderivative of this, it'll give us this. But remember, when you take an antiderivative, you have to have this plus c, because if we shifted this up or down, if we were to differentiate this, then when you differentiate something, the constant goes away. So the antiderivative of the blue function is the pink function. Hopefully that's not too surprising. But we get these rules, right? These are the different rules that you need to be aware of. And yeah, there's no point in me really trying to read them out. Hopefully have a look and make some sense of them. And jump on GeoGebra maybe and sketch them out so you can get a feel for why they're true. But this one is certainly, I think, a good example. Okay, so if we sort of jump into it to try and give us something to really think about. If we had a problem like this, so given the rules, so these rules here, which we just spoke about, evaluate f of x equals cosine inverse of x on a plus sine inverse of x on a. And I should have mentioned that a value is basically where your asymptotes are. So if we change a to be 1, then these functions, cosine inverse of x on a, which is in blue, and sine inverse of x on a go between -1 and 1. And yeah, so similarly, if we change it to 2, it goes between -2 and 2. And so the question is, see if you can pause the video using these rules and what you understand about them, see if you can work this out. And I think what you'll get, or you should get, if you work through that, is the following conclusion. So let's just step through this. So we can consider this its own function. If we were to differentiate both sides of these equations, so if we were to differentiate this whole function, we would get, well, if we took the derivative of cosine inverse, we took the derivative of both sides, we'd be left with -1 on the square root of a squared minus x squared. And similarly, if we take the derivative of sine inverse of x on a, we'll be left with 1 on the square root of a squared minus x squared. So you get this thing here. You'll notice that they are the exact opposites of one another. So they add to 0. So what that means is the derivative of this function is 0, which must mean it's a constant. So what would be interesting now is to find out what that constant value is. So it's basically a horizontal line in space, right? Because the derivative of this goes to 0. So that must mean it's a flat line, right? So since f dash of x equals 0, f of x must be constant between -a and a. And you can see, and you start to get a feel for the fact that if you were to add these functions together, I think you would agree that if you were to do the addition of ordinates, these 2 points here, if you were to add them together, you'd end up in the middle point here, which seems to be at this point here. So you can probably start to guess that we're going to get a horizontal line around here, like as well. Like if I move it up here, if I was to add the y coordinates of these values, we're going to end up here again. Okay, so you start to get a feel for it, and I won't hold you in suspense much longer. And I said it was down here, which was wrong. Need to be more careful. It's up here. It's at pi on 2, and I should explain. So if we were to go to this point here, if we look at the pink and the blue dots, they add to give the green dot at all points, and that's at pi on 2. So if we were there, for example, you add them together and it doubles it, because wherever they intersect, you're going to double it with the addition of ordinates. So yeah, you end up with this situation, which I think is pretty neat. And so yeah, if we just finalize this, so the reason we've substituted in at x equals 0 is because that just simplifies things. We could substitute in any value to find out what the value of f of x is at all points, because it is at all x values, the f of x is equal to the same value, which is pi on 2. So we just sub in 0 to make life easy. And we can see that sine inverse of 0 plus cosine inverse of 0 is pi on 2. And then this just says for all x between negative a and a, which is what we've got. So obviously if we change the values of a, we can stretch that out. All right, hopefully that's making a bit of sense. But yeah, I think it's an interesting property of antiderivatives involving circular functions, and that's sort of a nice way to test if you really sort of get what's going on, I think. So yeah, let's do one other thing, which is to look at definite integrals involving inverse circular functions. So maybe pause the video and see if you can work this question out. Evaluate the definite integral from 0 to 1 of 3 divided by the square root of 9 minus 4x squared. Now remember, if we want to take antiderivatives, it needs to be in this form. So you can see that we've got a situation where we've got a coefficient of 4 here. So you might want to think about how you can get rid of that, thinking about taking out factors and things like that. And you notice it's a squared minus x squared, so we need this first and second term to be a difference of perfect squares, essentially, or a squared minus x squared to be in that form. So if we have a look at the solution, as we said, we can take 4 out as a factor, and then so we'd have 4 underneath the square root. Square root of 4 is 2, so that can come right out the front, and so can the 3. So we end up with 3 on 2 out the front. All right, if we took 4 out as a factor of this thing in the denominator, we would get 9 on 4, but 9 on 4 is 3 on 2 squared, which is what we want. We need to find out what that a is. So that a is 3 on 2. And then we know that it has this form. So the antiderivative will be 3 on 2 sine inverse of x divided by that a value, which is 3 on 2. And we got to evaluate that between 0 and 1. And yeah, you do that. Remember, definite integral, sub in the upper bound and subtract the lower bound. And so you'll get this, and you'll need a calculator to work this out, but sine inverse of 0 is 0, I'm guessing. Let's check. Sine inverse of 0, yep, is 0. So that last term here goes away, and we're just left with 3 on 2 sine inverse of 2/3, which is approximately 1.095. And remember, this blue line here is this function, 3 on the square root of 9 minus 4x squared. So if we take the definite integral between 0 and 1, we're just finding the area between here, and hopefully, fingers crossed, we'll get that the area is approximately 1.09. So that's how you sort of incorporate definite integrals into your work with inverse circular functions. All right, hopefully you found that useful. Give us a thumbs up if you did. Let me know if you need any private tutoring or have any questions. Good luck with all your studies, and I'll see you soon.